for example number 7, we're taking the function f of x is equal to x squared plus x times e to the 2x, and we're going to use that series to find what the nth derivative of our function is at 0. So we start off with e to the 2x, just plugging in 2x instead of x for our series, for the usual e to the x. Then multiplying it by x squared plus x. This gives us two different series, and we want to be able to add them together, but once we take in those powers of x, we see that one has n plus 2 and one has n plus 1. We need these to match, so what we can do is for this first series, start it at 1, and we do the trick where if you increase where the series starts by 1, you decrease x everywhere else by 1. So increasing here by 1, decreasing everywhere on the inside by 1. So now instead of n plus 2, we have n plus 1 as our power of x, matching this one. Then for the second series, what we do is we take out the first term so that it'll also start at 1. So here we're just taking out when n is equal to 0. Maybe I'll write that down. And we're adding the series starting at 1. So nothing changes here, it's just the same series, we just took out that first term. Then we can combine both of these big series together into this one. This x in the front comes from the 0 term here. When we combine these two together, we see that we've got 2 to the power of n minus 1 over n minus 1 factorial here, and then 2 to the power of n over n factorial here. We can add these together into the same fraction by multiplying the top and the bottom of the first term by n, so then we get n factorial. But then the problem is we need to match this template here, we need it to be in front of x to the n. That actually tells us what our nth derivative is. And I think this was a mistake I made when I first uploaded this set of notes, so I'm going to replace that as soon as I finish recording this and go over this on Monday as well. So what we're doing here then is to have x to the n, we're again decreasing everywhere on the inside of the sum by 1 and increasing the starting index by 1. So here then, we instead of 2 to the n minus 1, we have n minus 2, and so on. Everywhere there used to be an n, we decrease by 1, so that we have x to the n. Now, the template that we want in order to find that general nth derivative at 0 looks like this. So we need to have n factorial on the bottom as well as at xn. So xn, but now we have n minus 1 factorial, and so we just multiply on the top and the bottom by n. I'll also note that times n over n. And that gives us then something that actually fits that template. And so then we can say that the nth derivative of our function at 0 is equal to this numerator here. And that is true for n, I guess, yeah, greater than or equal to 2. When n is 1, it's just 1, because that's what we have in front of the x there. And this is something we can check by actually just manually taking derivatives of our function and plugging things in. But that's how we find then the general formula. I just really want to emphasize that we need to fit this template here. So we need to make sure we have exactly n factorial on the bottom and x to the n, I guess, on the top, and then everything that's left over will be the nth derivative at 0. It's more important that we fit this part of the template than we start at the right place. You know, like, it's okay that we don't start at 0 anymore. It's most important that the inside fits that exact template. So I hope that's a bit more clear. I will, I think, go over this example again on Monday just to really clarify things. Okay, now example 8, we're taking a function f, we don't know what it is, but all we know is that its nth derivative at 0 is 1 over arctan 2 to the n for all n greater than or equal to 0. So this is all we know about our function so far. We also know that it's equal to its Maclaurin series at every point in its interval of convergence. So that means that we can actually just write f of x is equal to the Maclaurin series. So we just plug in, the general formula. We're given that the nth derivative at 0 is just this. And then we have it times 1 over n factorial, just again using the general template, then times x to the n. So this is just kind of plugging it into our general formula. For the interval of convergence, we just use the ratio test. Plug in n plus 1 instead of n. For this one is an. Calculating the limit, we get 0 for all values of x, because we've got arctan here. Both of these are just going to go to pi over 2 because we've got arctan infinity, arctan infinity. Because the bottom here goes to infinity, all of this goes to 0, so that's how we have 0. Because this happens for all x, then, the interval of convergence is negative infinity to infinity. This number 9 is a pretty involved one, and we'll be going over examples similar to this on Monday as well. So given the Maclaurin series for sine x that we've seen a couple times already, we can approximate sine x using just the first few terms. So you can say that sine x is approximately x minus x cubed over 3 factorial. First, we're going to use the alternating series estimation theorem to find the error of that approximation for x within the interval -1/2 to 1/2. Then we'll use Taylor's inequality to find the same error for the same interval. And then we're going to see what values of x the approximation is accurate to within 1 over 120. So if we look at the expanded Maclaurin series for sine x, we're really just taking these first two terms. And the alternating series estimation theorem says that the remainder is going to be less than or equal to the absolute value of the next term. So here, that's just 1 over 5 factorial times absolute value of x to the 5. Because our interval is specifically taking x between -1/2 and 1/2, we can say that the absolute value of x is 1/2. And so then the remainder is going to be bounded above by what we get when we plug in 1/2 here for x here. So that's how we get this, and that gives us a value 1 over 5 factorial times 2 to the 5. If you calculate what that is as a decimal, then that's just this number. So very, very small number. So that tells us that we're pretty accurate in that interval, I would say. If you want to use Taylor's inequality to find the error, what we do is we need to say what Taylor polynomial our approximation corresponds to. Now, because the highest power of x in this is 3, we can call it T3x, but because the Taylor series for sine x doesn't have any even powers of x, T3x is actually the same as T4x, because there's no T4 really. It's just, there's no x to the 4 term, so we can just say that it's also that. And the thing with Taylor's inequality is that we do actually get a different value for the error depending on if we use T3 or T4. And so in questions like this, you want to use the largest Tn that is correct to have a less conservative estimate. So we can say that sine x is our approximation, T4x, plus the remainder after that. By Taylor's inequality, the remainder after these terms is bounded above by m over 5 factorial times absolute value of x to the 5 for some m that depends on n, and here n is 4. Now that number m is the number such that our fifth derivative is less than or equal to m on the interval given. So this -1/2 to 1/2. The fifth derivative of x is equal to cos x, because here this is just, remember f of x is just sine x, right? So if you calculate all the derivatives, the fifth one will just be cos. Cos is always going to be less than or equal to 1, so we can just take our bound m as 1. Plugging that back into Taylor's inequality, we can say that the remainder is bounded above by 1 over 5 factorial, this 1 coming from the m, over 5 factorial absolute value of x to the 5. Then again, plugging in that absolute value of x is less than 1/2, we get this same number, same one as part A. So that's great. We get the same thing. Then by the alternating series estimation theorem, for part C, so part C again, we want to find which values of x the approximation is accurate to within 100 or 1 over 120. What we're going to do is just look at a bunch of we're going to look at that next term that we're excluding. So that was x to the 5 over 5 factorial. And we want to see what values of x make it so that x to the 5 over 5 factorial is less than 1 over 120. And we can just solve that inequality, and it turns out that 5 over 120 is equal to 1. So really we just need x between -1 and 1. So that's why this question had the 120 there, is just kind of a convenient canceling out. So yeah, for a question like this, you just set up your alternating series estimation theorem, less than whatever given error we want, and we use that to find the interval for x. And here I included a graph showing an overlay of the graph of sine x, which is in red, and then the graph of x minus x cubed over 6, which is in black here. And so you can see that because we're centered at 0, our estimation is really good near 0. And it's very good between -1/2 and 1/2. So that's this area here. As you get closer to 1, you can see that there is a bit more of a gap growing. And so based on our part C, we can say then that there's a gap between sine x and the estimation right here is probably about 1 over 120, just based on that calculation. So here you can kind of see a visual for what's going on. Okay, finally we've got number 10 here. And this one is an old final exam question I picked out just for us for practice. We're asked to find the Maclaurin series of the function f of x is equal to cos 2x and use the alternating series estimation theorem or Taylor's inequality, either works, to estimate the range of values of x for which the approximation cos 2x is 1 minus 2x squared plus 2/3 x to the 4 is accurate within 0.1. So this is pretty similar to the last example we did. Cos 2x, we just plug in 2x to the usual series for cos x. So that's there. We can rewrite it, take out the 2, so we can now have whatever the coefficient is. And then plugging in different values of n to expand the series, we can see that the approximation that we're given is just like these first three terms here. Same as last question, we can call this T4 or we could call it T5 because we can see that there is no power or fifth power of x there, so it's actually okay to call it T5x. And that will give us a less conservative estimate, but still accurate estimate for the range of values for x in which the approximation is accurate. So our function, cos of 2x, is the fifth Taylor polynomial plus the remainder. And by Taylor's inequality, that's going to be bounded above by m over 6 factorial times x to the 6. Taylor's inequality, it's always like if it's n here, this is n plus 1. That's something you can remember. We do need to find our m, but we know that cos is always less than or equal to 1. And so then the sixth derivative, if you calculate them out, I didn't write them all out here. The sixth derivative is -1 times 2 to the 6 cos 2x. That's always going to be less than, well, I guess if you take the absolute value, that's 2 to the 6, cos 2x, that's always going to be less than or equal to just 2 to the 6 times 1. So we set that to be m. So then, plugging that into Taylor's inequality, this 2 to the 6, we see that 2 to the 6 over 6 factorial times absolute value of x to the 6 is less than 0.1 if and only if. Then we want to kind of isolate for x to the 6. We get this number 9 over 8. And then we just take the 6th root to get our interval where the specified error, the 0.1, is accurate. So here again, we've got the two graphs. Again, red is cos 2x, and the blue one is the polynomial approximation we're using. And we can see that these curves are pretty close to each other, and the difference between them is that 0.1, exactly as far as we end up finding with this interval. So yeah, I guess we'll be going through more examples kind of like these on Monday. Hope this helps. Yeah, thank you.